to Decaf-Math. So today I am excited to talk about the idea of factorials. Factorials. And everyone who thinks about factorials has to get excited. Why? Because the symbol for factorial is literally an exclamation mark. Yay! Really just one, but factorials. So we put, for instance, 4 factorial. So that's how we would read this. Really excited for is 4 factorial. And what this means is we take 4 and we multiply by 3, then times 2, then times 1. Okay, so basically we take our number and then we decrease it by 1, by 1, by 1. And so these are going to be natural numbers. I'm not going to get too fussy about the wording there, about natural numbers versus whole numbers. Apparently there is not a consensus about this. In my background I learned that natural numbers are your positive counting numbers, so 1, 2, 3, 4, 5, and whole numbers include 0. But I do know that there isn't much of a consensus there because different textbooks and in school, different people seem to think different things about whole numbers and stuff like that, and if 0 is included or not. So it doesn't matter. Here we're just going to decrease by 1, by 1, by 1 until we get to 1. I can only handle one debate at a time, and I'm already trying to convince people that it's math and not maths. So really, the next debate about whole numbers versus natural numbers is not something I want to get into right now. But the idea is that we're only talking about, no decimals or anything here for factorials, and that we are just decreasing by 1 until we get to 1, and we are multiplying all of those. So 4 factorial is 4 times 3 times 2 times 1. So that's 4 times 3 is 12, times 2 is 24, times 1 is still 24. Okay, so notice that the 1 doesn't actually do anything to our product because 1 is the multiplicative identity. So it doesn't change our product at all, but it looks prettier, right? It looks pretty to go from 4 to 3 to 2 to 1. So we just leave it there. So 4 factorial is 24. Okay, so 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So just remember that it's all about multiplication. So 6 times 5 is 30. 30 times 4 is 120. 120 times 3 is 360. 360 times 2 is 720. 720 times 1 is still 720. Okay? So you can really do this with any positive number, and technically too, 0 is not positive, but you can still say that 0 factorial is 1. And if we wanted to prove this, there are actually a few ways to do it, I think, but I feel like this is one of those weird situations where you kind of work backwards. So it's kind of like when people try and prove that something to the power of 0 is 1. You kind of use definitions of other exponents and exponent rules to go backwards to show that it's 1. And I kind of feel like it's the same for 0 factorial. So a lot of times books will say 0 factorial equals 1 just by notation or just by standard. But there are probably a few proofs I'm thinking just straight up using permutations and the concept of permutations. I'm wondering, but also you could probably extend 0 factorial from using 1 factorial and just just the recursive definition of the fact that n factorial is probably n plus 1 factorial over n plus 1. It's kind of recursion here, but it's like backwards recursion, I guess, because you're thinking about it in the other direction. Like 1 is your base case, and then for 0 factorial, and then you can use 1 factorial is, you end up with 1 factorial over 1 to get 0 factorial. That's not totally satisfying proof, but it works. So if you have a way that you prefer to explain this, that's fine. I don't want to get too sidetracked from this video with this, but this is actually important to know because this would potentially be helpful for combination and permutation type questions. So, if you end up with a 0 factorial using one of the equations for those kinds of problems, you won't get stuck, or you won't kind of know what that is. It is 1, okay? So why do we really even care about factorials like this? Well, they're really handy in our permutations and combinations questions. So I don't want to get too much into permutations and combinations right now. I do have a separate video on that, and I will be making more. But the general idea with factorials is why it's handy is if you're trying to find how many ways like 3 objects can be rearranged, for instance, if you have 1, 2, 3 slots for the 3 objects and you want to know how many ways can you order them, let's say A, B, and C are the 3 items. To find how many total permutations there are, you're basically saying, okay, for the first slot I have 3 choices. I can pick A, B, or C. But then the second slot, once I've picked one, I only have 2 choices left, assuming I'm not going to repeat the letters, right, because I'm ordering them. And then the last one only has 1. So the number of permutations is 3 times 2 times 1, which is 3 factorial. So that's just like the basic idea, which is 6. And you can try that out yourself. How many ways can you rearrange the letters A, B, and C without repeating them? And I may end up writing out all of the different permutations and this kind of stuff in a sleepy math video, as though this isn't sleepy enough. But I'll do that tedious stuff in another video. But I just wanted to give you the idea. But when we're working with factorials, it's actually really nice, even though it seems like this is going to get really big, right? Imagine if we're trying to do like 12 factorial. 12 factorial is 12 times 11 times 10 times 9 times 8 times ... all the way to 1. That's going to be a really big number, right? So you can imagine how quickly things scale. However, what is cool about factorials is when we divide them, because a whole bunch of things can cancel. For instance, if we do 6 factorial over 4 factorial, like that. So 6 factorial, we already did this, it's 720 over 24. But what is cool about that is if you look at 6 factorial being written out here, 6 times 5 times 4 times 3 times 2 times 1, you'll see that this 4 times 3 times 2 times 1 is actually 4 factorial already. So if I write 6 times 5 times 4 times 3 times 2 times 1 all over 4 times 3 times 2 times 1, because it's all multiplication and division here, we can have some canceling fun. So 4 and 4 cancel, 3 and 3 cancel, 2 and 2 cancel, and 1 and 1 cancel. And why do they cancel? Because we are multiplying. So if this were all addition, that would not work. You can only do it for multiplication. And it's really because you can separate out the fractions if you really want to think of it that way. 4 divided by 4 is 1, and anything times 1 is itself. 3 divided by 3 is 1, etc., etc. Okay, so all you get is 30. It's just 6 times 5, which is 30, which is correct because 6 factorial we already did. 720 divided by 4 factorial is 24. So that is 30. Correct. Hooray. So that's the cool stuff with factorials, is you can actually cancel things. So with a bunch of practice, you can get the hang of it. Like, things can start canceling pretty quickly. Like 13 factorial over 10 factorial. Even if you don't have to write every single number, you know, you don't have to write 10 times 9 times 8 times 7. You can just kind of visualize it. You'll see that 13 factorial is 13 times 12 times 11 times 10. Maybe, you know, you write a few extra terms to 1. And then 10 factorial is 10 times 9 times 8 times dot 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 1. So if I write the top numbers, I'm kind of just keeping in mind that I'm dividing by a 10 factorial, so I know everything past 10 is going to get canceled out. See, including 10 itself. So dot dot dot, so 8 would cancel with 8, 7 would cancel with 7, 6, 5, 4, 3, 2, 1. These would all cancel. So basically all you're left with is 13 times 12 times 11. So see, you don't actually have to multiply out 13 times 12 times 11 times 10 times 9 times 8. You don't have to find what 13 factorial is in this question to do 13 factorial over 10 factorial, because everything beyond, like, the whole 10 factorial gets canceled out. So really this answer is 13 times 12 times 11, which you can do. 13 times 12 times, did I say 10? I don't know, 13 times 12 times 11. So 1716. If that makes sense. I hope that makes sense. So in other words, like, maybe at first you can prove to yourself by writing out all the numbers and then canceling them out, but after a certain point you'll just start to get used to the fact that you don't, like, everything else cancels, so you don't need to worry about it. So this might help, this idea of factorials might help for finding the NCR, like finding the number of combinations. So let's just work through one. The formula for n choose k. I don't want to introduce all of this new notation for those of you who like to learn in chunks, but this is basically a hidden factorial question. This means n choose k is n factorial over n minus k factorial times k factorial. So this is like factorial happy. But this is when you have two numbers. So choose n choose k. So for instance, 8 choose 5, like this. This is n, and this is k. So you just plug into this formula here. N is 8, so 8 factorial over 8 minus 5 factorial is 3 factorial times, so times, because it's smushed together, so times k factorial. So that's what this means. And so now that we know how to work with factorials a little bit, this 8 factorial is 8 times 7 times 6 times 5. And I'll just go ahead and write it out just so that we can see what cancels. But in general, you'll get the hang of doing this in your head. But 3 factorial is 3 times 2 times 1. And then 5 factorial is 5 times 4 times 3 times 2 times 1. And because these are smushed together, you just multiply. So 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. And now you can cancel everything. 5 and 5 cancel, 4 and 4, 3 and 3, 2 and 2, 1 and 1. And 3 times 2 is 6, which cancels cancels with this 6. So this whole thing is just 8 times 7, which is 56. If that is not satisfying, I don't know what is. I love factorials because things just cancel. So 8 choose 5. This whole complicated formula is really just 56. So factorials are so nice because you're really just multiplying stuff, and when you're multiplying and dividing, things cancel nicely. So one last little point that I wanted to point out is try to resist the temptation that, like, 4 factorial plus 6 factorial, for instance, is not 10 factorial. Okay? Resist the urge. So factorial itself is not just like, you can't distribute it. Like, you could probably find some cool patterns. It's been a while for me, but you could probably use this definition originally to find some cool patterns and proofs. I do know a lot of convergence proofs and stuff have to do with this, like whether a series converges and you use the n+1, you find the ratio test, blah blah blah. But I guess I should also point out the algebra equivalent for this kind of question. So when we need to simplify and divide stuff with algebra, so if we're using when we're using factorials with algebra, for instance, let's say we have n+3 factorial divided by n factorial or something like that. So now if we have like an algebraic thing to simplify, you can do the same thing as we were doing before with numbers. We just need to be clever with how we write this out, right? If you can visualize it yourself and do it in your head, that's fine. But if you want to write these terms out, notice that n+3 factorial is n+3 times n+2. And then really in algebra you don't use times like that anymore because that can look like x. But you're really just multiplying n+2 times n+1 times n, right? So you're just decreasing by 1 like you normally would, right? So then you times n-1 times n-2 dot 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 until you get to 1. Then that divided by, and then n factorial is n times that number decreased by 1 times that number decreased by 2 dot 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 to 1. So we didn't really directly say, but if I'm going like 4 times 3 times 2 times 1, right? You can think of it as -1, -1, -1, but you can also think of it as 4 times 4 minus 1 times 4 minus 2 times 4 minus 3, right? So that's the same thing, because you're basically minusing 1 and then -1. So that's -2. So if you wrote it this way, then you can still do your normal canceling. N and n cancel, n-1 cancel, n-2 dot 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 to 1, and 1's cancel. So you just have n+3 times n+2 times n+1. And so you don't really need to write every single term in between here because you don't know what n is, right? So we're just going to generalize it. We can just put that dot dot dot, but really, you know, depending on what n is, this could be 1, or this could be 1, or this could already be 1. Actually, this can't be 1 because n has to be 0 or more, right? But hopefully you understand what I'm saying. Like, you can just go dot 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 to 1 to visualize what's happening, to see which terms cancel, and then your answer would be n+3 times n+2 times n+1. Oops. Times n+1. And then just depending on, you know, what the actual question is, if you're just trying to simplify this, that's fine. And you could expand that out if you want. But I just wanted to show you that this can work algebraically. You just might need to be a little bit more clever with how to express the -1, -1, -1. but it works exactly the way that you're doing it before. So anyways, I hope that this was a fun little introduction to factorials. This notation here is basically the idea that you can think of it as like the number minus 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 down to 1, but you can actually work the other way around. So for instance, notice that for 6 factorial, if it's 6 times 5 times 4 times 3 times 2 times 1, that's the same thing as 6 times 5 factorial, because the 5 times 4 times 3 times 2 times 1 is 5 factorial. So 6 factorial is actually 6 times 5 factorial. And that's this general equation here. It's just if you rearrange this algebraically, you'll see that 5 factorial is 6 factorial over 6. That's what this thingy means. It's like looking at the next term and seeing that it's really just your number times the factorial of the previous number. You could do some cool algebra stuff with that if you wanted, but I hope that this was fun and kind of interesting. It seems kind of random right now, but I wanted to review it for those of you who have learned factorials before, needed a little refresher, and if you are new to this and are interested, let me know. Right now I'm just kind of bouncing around topics, but the more feedback that you give me, let me know what you're interested in, and subscribe if you want to hear more math videos, and don't hesitate to let me know if you're like in a particular class, you kind of want to go over something. I'd love to just hang out and do some math. So I hope that you had some fun. Thank you so much for hanging out with me, and I'll see you soon.